So yes, I'm going to be talking about quantum Walk combs. And, it's a story about optical sources. And in a sense, the take-home message I will try to sort of explain today is that quantum Walk comb is a natural comb generation mechanism for semiconductors. But I will, of course, start from a bit before. And, in the beginning, what we're talking about is obviously lasers. And for lasers, what you need is, of course, those three optical processes that were postulated by Einstein. And especially what we're interested in is the situation where, because of the symmetry between absorption and stimulated emission, if you have more electrons in the upper state than the lower state, then you can amplify light. And if you can amplify light and maintain that population inversion, you basically put your system in a resonator, and then you have a laser, obviously. And now, if you want to measure the frequency of this laser, and if you have a reasonably monochromatic source, there are many ways of measuring frequency of lasers, but one which I will be interested in discussing more today is the one where we're doing so-called heterodyne measurement. And that's it. It's basically doing with optics what you do with radio waves, is that you take two of your signal frequency lasers, you mix them onto a detector, and as you would have for the beating between instruments, in the audio range, what you can detect here is the beating between those two frequencies. And obviously, that beating now occurs at the difference frequency between those two sources. And if your sources are narrowband enough, then of course that beating will appear in your electrical spectrum as a electrical beat note. And of course, by measuring the frequency of that beat note, you actually can measure the frequency, the difference in frequency between your two lasers. Sorry, I'm struggling with this guy, but okay, doesn't want to go. Okay, whatever. And so let's say this is, of course, a very old idea, and it was already demonstrated many years ago by the inventor of the Heaney laser, Ali Javan, who already showed at the time that, if he took here two, what he called at that time masers, which were, of course, the original microwave amplification by stimulated emission, before they called them lasers. He took two of those devices, mixed them into a single detector, and observed that nice little beating in the electrical spectrum. And this idea that you can take frequencies in the optical domain and bring them in the microwave domain is basically the basic idea behind a comb. And a comb, an optical frequency comb, is an optical source that generates frequencies that are nicely equally spaced in the optical domain, and also where that spacing is basically in the frequency range that you can detect electronically. And in this way, the beautiful aspect of such a comb is that you can, if you want, label any tooth of that optical spectrum by by one integer and two numbers. The integer tells you which comb tooth you have, and the two numbers are the spacing between the comb line and, of course, the so-called offset frequency, which means where that first line is compared to zero frequency. And if you specify those two numbers, then with the integer, you know exactly where the frequency of your line is. And of course, this is a fantastic invention because, and that's why, of course, Ted Henge and Jim Hall got the Nobel Prize for it, because it allows you now to connect optical frequencies and radio frequencies seamlessly. Once you have those two numbers, these two offset and repetition frequency are measured electrically. And therefore, you can do two things. You can either go from the optical domain down to the microwave domain, and that's optical metrology. And that's why, often-wise, those combs are depicted by gearboxes, because you think of that optical frequency as the very fast spinning gear, and then you have this slow spinning frequency, but the gearbox tells you, it kind of converts directly this optical frequency into electrical frequency, but you can also go the other way around. You can start from a microwave frequency and basically impose, if you want, create an optical frequency with that. And we will be more interested in that second process in the type of combs I'm going to be describing. But the comb itself, so far, really the only property that I've been kind of discussing is the fact that the comb is created by these equally spaced frequencies. But I've not said anything about what are the relative phases of those different components. So the only thing, in a sense, we're saying is that the envelope of the intensity is periodic. That's the only thing you can safely say. And now you can actually think, what does it look like in the time domain? And in the time domain, it can actually have different pictures. And of course, most people are used to combs as being created by regular pulses that come with, heavily periodic. And that's, of course, one possibility of creating a comb. But it's not the only one. You can also think that you create your comb with all those frequencies and you slowly change the phases as is shown, and you see that the intensity of the comb as function of time now changes. Instead of being just a pulse, it becomes almost continuous wave. If now you see, if you, in the left side, you basically had the mode number, and each mode number had a different phase. And now if now the phases are not the same, but are parabolic, you see that the overall intensity is such that you may basically have a constant intensity with that. And that, means that you can have those two types of comb. But to create the comb, you need, of course, to really realize that it's an optical system. It is, of course, a physical system, so there will be noise. And therefore, a comb is not just a source where you mechanically aligned n lines such that they are each independently tuned to exactly spacing. No, what you have is you have some process, a nonlinear process that locks those modes together. And that, of course, that nonlinear process is essential, because now it means that if you have a fluctuation of your comb, the comb can either fluctuate like that or fluctuate like that, but it doesn't have fluctuation of independent mode against each other. And that, of course, is very nice, because it means that when I beat this comb onto a photodetector, I can have a very, very narrow line. And just to remember, how do you lock modes? Well, you need a coupling. And you need to couple those modes together. The first example of mode locking was demonstrated by Christian Huygens, who showed that if you take two clocks and you mount those two clocks on a shared board, even though there's a tiny coupling, if those two clocks are reasonably close in frequency, they will lock together and just oscillate exactly in phase. And here, of course, what we want to do is basically do the same thing, but of course we need to do that across different frequencies. And historically, the first way that people have locked mode together is basically by doing what is so-called, of course, a mode-locked laser. So how does a mode-locked laser work? Well, a mode-locked laser, you basically start from a gain mechanism, a cavity, a fiber-pro cavity, in which you have your gain in green, and that you assume so far that this gain is very slow. We'll go back to that thing afterwards. And now what you put is inside the cavity somewhere is a saturable absorber. And that saturable absorber is a two-level system which reacts that if you have a low intensity, it absorbs a lot. If I have a large intensity, the two-level system is saturated, and then it reflects efficiently. So now what happens is, if you have a competition between having inside your cavity a continuous wave operation, that will induce a large loss, so it will not lace that way. If you have a pulse, however, the pulse saturates the saturable absorber, and therefore it's favored. So with that technique, you can actually lock modes together. And that's what people have been doing for a long time. Now, it turned out that, as was said, I worked on quantum cascade lasers, and I will go back to that. But one thing of the quantum cascade laser, it's not a slow gain. And what we realize is that despite the fact that it's not a slow gain, and therefore there was really not much hope to have a pulse circulating in there, we realized that those devices, they actually generated combs. So at that point, I will not go in details how it works. It worked mainly because you had what is called four-wave mixing processes that would tend to lock the modes together. But I'll go back to that. What I want to say is that, well, those modes were those lasers were actually can be made very powerful, up to a watt in that case, operating comb with a watt. You can see that the beating between the modes gives you this very nice and sharp beat note in electrical domain, meaning that the modes are really locked together, and you basically have more than a milliwatt per mode. What can you do with this? Well, what you can do, and that's what got me into being interested in combs, is you can do so-called dual comb spectroscopy. And dual comb spectroscopy, the idea is you take two of such comb, and in the optical domain, you will have the comb 1, which is the black lines, and you have the comb 2, which is the green. And those two, you made them such that they don't have exactly the same repetition rate. That's slightly different. And now what happens is if I shine those two comb sources onto a detector, each pair of line will create a different beat tone at a different electrical frequency. Now, what I've done with this, I've mapped the optical frequency domain into the electrical domain, because for each one of these lines, I will create a new beat tone. And if now, of course, I'm able, if I'm going through some molecule that absorbs the light, well, that absorption will decrease the intensity of that mode. And of course, I will see it on my RF spectrum. So this way, I'm able to do a spectroscopy, which is very broad because it's as broad as your comb, in a purely electrical way. So you don't need a mechanical stage, you don't need a grating, you don't need anything else. You can do that in situ. And why is that useful for? Well, one of these useful for is for detecting chemicals. And the idea of a chemical optical detection is that you send your laser light across the gas, or let's say the chemicals that you want to detect. And if you do that in the mid-infrared, where you have very strong lines, you can actually here, this is an example of detecting CO2. You can even, because what you're doing is you're probing the mechanical vibrations of your molecule, the vibration frequency of that molecule depends not only on the chemical species, but it also depends on the isotope. So you can even detect which isotope you have into your gas and how much of each isotope you have. And there, of course, this spectrum is given by a single frequency laser. But now, with that single frequency laser, you can already be sensitive to this chemical and isotopical content. But the idea is, well, maybe with my dual comb, I can do exactly that same measurement, but over a much wider frequency range, because usually the very narrow band, the so-called distributed feedback lasers, so the single frequency lasers that we're using for doing this type of spectroscopy, they cannot be tuned over a very wide range. They can be tuned like shown here, a few inverse centimeter maybe. But the comb, they can be 60, 100 inverse centimeter. So in principle, you can do spectroscopy over a much broader range. So this works. Here, of course, it's a bit of a busy graph, and I don't want to spend and explain everything that is in there. The idea here is that this experiment contained two quantum cascade lasers. Each one was operating as a comb. There is a multipass cell, so which is this thing called MPC. It's where you basically sample the gas. And then there is an additional thing, which is there is an additional laser on the side to measure which frequency is, because you're moving your combs, and then you want to remember where you started from, if you want. Huh? And in this way, okay, it's a fairly complex system, but in the end, you see that you have the two combs, the red comb and the orange comb. You see that you have a single frequency DFB, and the blue thing is what you observe on your spectrum analyzer, the electrical signal in one, where each one of this line here that you see is corresponding to a special beat note. So anyway, long story short, what is really impressive is with that system, you're able to detect, and this is of course not my work, this is work done by a group in Zurich, in EMPA, led by Lukas Emmenegger, and this is the paper. And what they did here is they measured, you see, over more than 40 inverse centimeter, which is, more than a terahertz and a half of bandwidth. And they measured with a point spacing of a megahertz or below, and they're really able to measure this extremely fast. So this dual comb technique used this way is really unique in how fast and accurate you can actually measure and do spectroscopy. And well, this also was transferred to the industry through our spin-off IR Sweep, which was was spun off, and then the whole technology was sold to Thorlab, so it's a commercial product. But all is not perfect and great in the world of dual comb spectrometers. To be honest, finding two quantum cascade lasers that operate as a comb with a bandwidth that overlaps well and they are stable, this is not so easy, and that's something we're still struggling. And that's why, in a way, you can think we went back to the drawing board and thought about how can you make combs? And that's basically where the quantum walk enters. And that's why I'll start from this quantum walk, and I will really highlight the work of these two people who worked in my group, Ina Heckelman, who just completed her PhD brilliantly, and my postdoc, Alexei Kopoltsev, and who just got an ERC. So they're really fantastic, both. And so what is a quantum walk? First of all, if you talk of a classical walk, is a well-known conceptual question where you say, well, imagine someone who at each step randomly decide to go left or right, and would be a drunken. And the question is, okay, how far does he move after n steps? Well, and this is, of course, an important process in all statistical physics. And was, of course, Einstein, studied this in the context of the Brownian motion. And now the idea is that, well, if you do z, if you move z steps, you're going to effectively have a distribution that broadens like square root of the number of steps. And and then the probability, the density probability of being, at certain distance is basically a Gaussian. But now you can ask yourself, okay, what happens is instead of at each step moving as a classical particle, which has to choose whether it goes left or right, but I can think, well, maybe I'm a quantum particle. And if I'm a quantum particle, I can basically go both ways, and I just split my wave function, if you want. And that is, of course, for this reason called a quantum walk. And there, of course, the result is very different, because at each step, you actually can both sides. And because of that, when you compute the probability distribution as function of time, well, number of steps, you get this fact that the width of your distribution grows like the number of steps, and the distribution is basically the one of a Bessel function. And this has, of course, been intriguing experimentally, and people have thought, okay, can we sort of emulate those quantum walk in real systems? And if you think about a quantum particle, in a way, a photon is a nice one because it's easy to make, and it really behaves as a wave. And so people, for example, have done this coupled waveguides where the idea is that you send light in a waveguide, and it can choose to stay on the same waveguide or couple to the next waveguide, and so on and so forth. And in this way, you can see that with coupled waveguide, you can move, and you see this distribution that you would expect. It's been also done in 1D or 2D in free space. But what I would like to discuss is not a quantum walk in the real space, but I would like to describe a quantum walk in what we call a synthetic space. And the synthetic space, you can guess already why we're doing that. Our synthetic space are the modes of a circular a circular resonator. So imagine I have a waveguide that makes a circle. Then you know that, of course, any standing wave is a solution of that waveguide. And then you can basically list all the solutions which will have wavelength, which are just integer fractions of that length. And now you can think of, well, if I look in the frequency domain, those modes are equally spaced in frequency. And you can think of those as being now the various point that over which I'm going to be doing my quantum walk. So now I'm doing a quantum walk in frequency space. So, well, of course, here just a little thing which is important is, of course, if you're not looking at those modes, if you consider all the modes of a ring resonator, of course, you can have a right propagating mode or left propagating mode. So for each frequency, you would have two solutions. But we will consider only one of the two, and that's an important detail. So now you can also remember that, well, those modes are not really often wise. Of course, in all real systems, there will be dispersion. And dispersion means that the frequency spacing between adjacent mode, if you want, the refractive index changes with frequency, and therefore the spacing between the modes changes slightly with index number or frequency, and therefore you can think of this as, now it's not anymore a ladder which is exactly equally spaced, but it's a equal space plus a quadratic term, and we're just going to subtract the constant term and just keep the quadratic term. But now, and then of course you can sort of, we'll see, of course, those who are familiar with the Hamiltonian description, we say, well, here we can say, we now have each one of these sides has a frequency, which is given by this m square, and the d, which gives me a curvature of my parabola, and then I can create a photon in the m site using this creation operator. And then, now, we want to do a quantum walk. So how do we do a quantum walk in frequency space? Well, to do a quantum walk in frequency space, what you can do is you add a phase modulator that you actually drive at exactly the resonant frequency between two adjacent modes. Now, that phase modulator, what it does is, if you remember, if you take a single tone and you do phase modulation, well, you create tones that are at multiple frequencies of that modulation frequency. So if I have a mode that is circulating in one direction and I apply this resonant modulation, well, what I do is I'm going to send that mode in up frequency and down frequency. So now you can start to see, well, I have my parabola and I now have something that makes my mode hop. So far, it looks like indeed, it could be indeed a quantum walk, because effectively I do have this Hamiltonian where I sort of can create, of course, a mode at some pace, and then I can make this mode hop via my modulation with certain strength. And you can even think, well, how far can I go up? Well, and you can, of course, because the problem that you have is, remember, I'm modulating at the frequency which corresponds exactly at the resonance in the center. But as I move away from the center, my frequency becomes more and more detuned from the spacing between the modes, because I have this parabola. And now you can just work the algebra and you find that indeed there is a maximum place I can reach after which I'm too detuned and I cannot go up. So that gives you kind of this, we can call it in that picture, this maximum kinetic energy. Think of it as a kinetic energy because we have a parabola, and I can think of it as a parabola. Now, so that defines, let's say, the maximum width of the bandwidth of my comp. But now we want to add another ingredient to our model. And this ingredient is the fact that we want to do not only the phase modulation, we want to have this ring, but we want to have those modes that self-sustain. So we're going to put gain. And the gain, what it does is, of course, makes the thing laze. And now, remember, how does a laser work? Well, what you do is, of course, you pump your gain medium, you reach the gain above the one that you round-trip gain that you do to circulate one laser. And then, of course, what happens is the light builds up inside the cavity, and the building of the cavity, of the light in the cavity, basically, eat away, if you want, some population from the upper state, and the gain decreases, and now you basically have this gain that so-called saturate with intensity. How does that work in ideally? You say, well, when I start my laser, I have this gain, and that gain, of course, depends on frequency. So you have a maximum gain, that's where you're resonant, and then it decreases. And now, of course, if I start to have one laser at the mode that has the largest gain is the one that is closest to the peak of the gain, will eat away all the gain until the gain is exactly equal to the losses. Because, of course, if the gain is larger than the losses, the light goes up in intensity, and therefore it eats more population. Now, right, this is, of course, what happens. So in our model, we can say, well, we can think of the gain as, if you want, I'm losing particles with an imaginary part of the Hamiltonian. Okay, that's one picture, but let me discuss it in a bit of a different picture. I'll just show this, this equation. So what happens when I described it with words before, I can describe it with an equation saying that if I look at a population of electrons n, if I have a population of photon inside my cavity, that population of photon, because of the stimulated emission, will decrease the upper state population. And of course, what is critical here is how fast is that gain recovering? So how fast it loses compared to the photon lifetime. So those are the two numbers we need. If you want, the idea is, can I sort of think of my gain as being something very slow, and it will not realize that the intensity varies quickly, or on the contrary, the gain sees the intensity fluctuation. So look, let me show you why it's important. Imagine that I have a gain inside my material, and on the left, I have a fast gain. On the right, I have a slow gain. And now I send a pulse in my cavity, and I see what happens. So what happens is that the fast gain, it saturates the gain exactly at the peak, and the gain recovers just afterwards. So in the end, the gain, the intensity is actually, the pulse is always depleted at the place that the gain is, let's say the gain is lower when the intensity is higher, so therefore it's less amplified. So in the end, the peak is basically swallowed, and I, in the end, have a constant intensity. Whereas if I have a slow gain, the material has no time to respond, and the peak, the pulse continues to propagate. So now, you see, the question is, what happens when we actually apply this gain, slow or fast, onto my quantum walk? So the idea is I turn on my quantum walk, and I apply gain, and I see, let's say, what happens with time. Well, what happens with time is, if I have a slow gain, I have one thing. Of course, I want to expand my quantum walk, but as I'm moving my modes further and further away from the peak, they have less and less gain because they are in the region where the gain is smaller. So they are kind of eaten away, and in the end, I'm left with this Gaussian pulse. And in the end, if I look at my solution of my Hamiltonian, which is this parabola, you can say, well, what happens is that initially maybe you start with a single frequency, which would be in one lattice site in the center, and as I'm moving with time, actually, I'm going down in the energy states, and in the end, I finish with the ground state, which is a parabola, which is the Gaussian pulse. So, and of course, ultrafast gain system will be different. So let me see what it looks like in the frequency domain. So this is a simulation in the frequency domain of what happens. So you see the mode propagates, but then you see on the gray is the gain, and then you see the gain is, of course, let's say, is of course weaker in the, and this is the average. And so what you end up with is, of course, a pulse. You see in the frequency domain, you have this parabolic, this Gaussian distribution. In the time domain, we can look at now the same simulation, but in time. In time, what you have, and then you look at, of course, the time in periodically, what happens is that as you broaden, of course, you still have intensity everywhere, but now you see that the intensity which is at the peak of the gain is, at the peak of the modulation is favored. And so we basically have this one peak, because you see, what of course is important to remember is that if you have the frequency and time are related by Fourier transform. So if I have a Gaussian, which is my solution in the time, in the frequency domain, I have a Gaussian in the time domain also. So a Gaussian in time domain means I have a pulse. And that is, of course, a well-known thing. This is 1970. There was this paper by Hermann Haus, who already had made this. He didn't call that a synthetic dimension yet, but effectively he had done exactly the same thing. He had shown that if you do a modulation, a phase modulation at the round trip frequency of a system with a slow gain, you basically, he said clearly that let's say that the higher order Hermite Gaussian solution of the synchronous sinusoidal modulation are shown to be unstable and hence unrealizable in the steady state. And so his message was, you have this harmonic potential, you have all those solutions, but the only one you need to care about is the ground solution, because it's the only one that is stable. And that's why, of course, it's nice because you have a Gaussian pulse, but what is not so nice is that you realize spectrally in frequency, this is a very narrow band. It's a very narrow band spectrum, and therefore, of course, the pulse cannot be very short, because if you have a narrow band, narrow band spectrum, you cannot have a very short pulse. And that's why it was always understood that if you have an actively mode-locked laser, you can only have relatively long pulses. But now, okay, and this was, of course, described in the famous Sigman book and so on. But now, you can ask yourself, okay, what happens if I have a fast gain? If I have a fast gain, I know my system will not want to have a pulse. I showed you before, if I send a pulse in a system that has a fast gain, the gain is saturated during the pulse, so the gain is basically eaten away and go back to continuous wave. And if you do the simulation, what you observe is that you have, of course, the quantum walk, and then it stabilizes. And if I show now the simulation in the spectral domain with a fast gain, you see that you expand the comb, it gets broader and broader, and at some point, of course, you're reaching kind of this maximum, because at the edge of the comb, the detuning becomes too large, and then you stabilize. So now you have a much broader frequency range. And in the solution, it meant that instead of going, let's say, down, I'm going up. So now if I look in the time domain, you see, when you start, you have this gray line, which is this constant intensity, because you have, of course, a single mode. And as I add frequency and frequencies, well, you get this little kink, but more or less, you have something which is constant intensity. So what you have now is you have a comb, which is very broad spectrally, but basically with a flat intensity. And this is what you sort of predict. If you have a fast gain medium and not a slow one, you apply your modulation at the center frequency. What you see is first a quantum walk where you expand, and then you basically stabilize the comb over this very broad frequency range. And of course, remember, there is one thing which is nice, you can immediately remember, is that you can expand, the amount that you expand is directly proportional to how strong you modulate. And because if I modulate stronger, I couple, and I can go, you see, it's always this comparison between how much I'm detuned to how much I actually modulate. And of course, the more I modulate, the more I can, if you want, go outside the center detuning. Now, why is it that especially relevant in quantum cascade lasers? You see, quantum cascade lasers, what you're doing is you're using inter-subband transitions in quantum wells. And quantum wells is the very thin layer of semiconductor of narrower gap into a semiconductor with a wider gap. And as a result, what you have is you can now, by changing the well width, you can change the spacing between the energy levels. But those energy levels are only defined in one dimension. In the other dimension, you have parabola, because electrons are free to move in the plane. And therefore, you have always this nasty little purple arrow, which means I can change from the upper state to the lower state. I don't need to emit a photon. I can do that horizontally by emitting a phonon or scattering elastically. So, of course, one thing which is, one thing which you have here is that the lifetime is extremely short. It's below picosecond. So this is definitely a fast gain. Now, what we did is we took that material, made it into a egg-shaped laser, and I don't have time to discuss in detail, but it's basically to extract the light a bit more easily, because the light is emitted by the bending losses of your waveguide. And what happens is that when you take that laser and you turn it on and you don't do anything, you can basically see that you have, depending on, let's say, which direction you look, you can have, of course, high power or very low power. And what happens is that the laser naturally will break symmetry. That means it will naturally, automatically, it will decide, I choose one direction and I laser in one direction only. And that is something called a spontaneous symmetry breaking that arises simply because you have an extremely clean waveguide with very little backscattering. And as a result, what you have, if you don't do anything, you have a device which is completely single mode and remains single mode all the way to the maximum current. So pretty boring. And why do we have this spontaneous symmetry breaking? It's because we basically have counter-propagating mode that basically, if you have two counter-propagating mode, you have a grating, because you have beating between those two modes that are, you have basically build up a standing wave. And of course, the gain is eaten more in the peak of the gain, and it's not eaten in the bottom, let's say, where you have high intensity, you're eating away the gain. In the low intensity, you're not eating away. And therefore, what happens is that you have less gain in general for the light which is running, and therefore the system prefers to decide, well, let me go in one direction. In this way, I'm basically using the gain better. But that's, of course, spontaneous. So now, of course, what happens is, do we have a quantum walk in the system once we apply the RF? Yes, we do. And we do because that's what we were expecting, of course, to see this quantum walk and then stabilization. And that's what you observe in experiment. So it's shockingly, the agreement is really shocking. Because what we did here is the experiment, we had this laser, which was single mode, and we simply turned on the RF modulation and measured the spectrum after some time. We do that by stroboscopic technique, of course, and we use the fact that the system is very repeatable, but the agreement is really, really good. And that really shows that we have this quantum walk dynamics. Now, the other thing that we were predicting from this quantum walk model is the fact that when you apply an RF modulation, the quantum walk broadens, and the width of that spectrum depends on how much power of RF you're injecting, and that should grow like the square root of the modulation depth. And indeed, here is a set of spectrum as function of increasing RF power, and you see that we indeed follow the square root dependence that we're expecting. The square root dependence, of course, depends on how tight your parabola is. Of course, if my parabola is very flat, it's very easy to go up. If my parabola is very tight, it's very hard. And here we had two devices with two different degrees of dispersion. So with stronger dispersion, it was harder to go up. We had another device which had almost zero dispersion, and this one broadened very quickly. And the last thing we could check, and this is, okay, I don't have time really to discuss that because it's a bit more involved, but it's, okay, what happens when you don't inject exactly the center frequency? You don't really are perfect in resonance. So if you are very off resonant, then you have a situation which is known from laser physics of the 60s. It's a called FM laser. And if you drive, if you modulate, if you phase modulate a laser really way out its center frequency, what you can show is that you have a spectrum which is kind of a Bessel function. And the instantaneous frequency is basically sinusoidal with time. Now, if I'm actually exactly resonant, which is the second panel here, if I'm absolutely resonant, I have that let's say the spectrum has this very funny, half cosine shape, and then it resets. So the instantaneous frequency jumps abruptly and then goes back. So you have this frequency that sort of is not linear with time, but it's a half cosine and jumps back to. And then you have intermediate states, which I don't want to discuss. But see, what is really very interesting is to show how well the predictions and the experiment match. So this is resonant quantum walk, and this is kind of the intermediate regime. So now, what can you use those quantum walk for? Well, of course, you can do dual comb spectroscopy, as I showed before, and this is if you're work in progress. But there is one thing which we did, which is even more interesting. If you look a bit carefully at the middle curve, at the intensity as function of frequency, you see that the spectrum changes a lot depending on what is the frequency that you're injecting compared to the reference. And so you could say, well, can I use this? Because there are not so many systems where you can take a comb and shape the envelope of the comb at will. And there, the idea was to do a so-called single comb spectroscopy. And it's a bit the same idea as what people called lensless imaging by compressive sensing. The idea is, imagine you're trying to make an image, but you don't have a camera. So I have only one pixel detector. So what surprising thing you can do is you can take this single pixel, and what you can do is put masks in front of the detector and putting a lot of different masks, and each time measuring the intensity. And if you do that well and you have enough masks, and that mask effectively build a kind of a basis in your state, you can actually reconstruct the whole image by knowing how much intensity you hatch for each mask. Here, of course, when you do spectroscopy and you try to measure the spectrum, it's a bit the same idea, except, of course, initially, when you take a single mode laser and you scan it, it's very trivial because you're moving the frequency linearly. What we want to do is take that system where you say, well, what I do is I have a property, intensity as function of frequency for different position, and I transmittance, and I get the integrated intensity. And now what I want to do is, of course, take now a system where I have my source, I know what it is emitting, and I measure the intensity for different shape of my spectrum, and I go backwards. So having measured those intensity, I can sort of infer what was the spectrum. So here, the experiment is we have this quantum walk, and we have an interaction cell. We can check what the spectrum is, and we can use a detector. And so what we do is we scan rapidly the laser as function of frequency. And by doing this, we basically know for each injection frequency what the spectrum is. And now we know our ground truth, if you want. And now what you can do is, of course, you can see that as you scan now as function of time, and this is an absorption of a, acetone molecule, and you see that you can predict, of course, going forward, meaning you know your spectrum, you know what your transmission should be, and you can compare whatever you measured with whatever you computed, and you see that we have a good agreement. But of course, now we can, look and understand that, of course, depending on if I look, of course, if I take the various spectrum, if I'm, for example, at the beginning, then if I'm off resonant, the spectrum is in here, so it's very strongly absorbed. So that's why I have a low intensity. When I'm in the middle, then the spectrum is very broad, so you have a lot of intensity that goes around the absorption peak. That's why I have more transmittance. And so this is basically my, if you want, my finger print. So now we can do and try to see what happens if I have, for example, a mixture of two molecules. And a mixture of two molecules, like acetone and 2-butadiene, I can get, of course, a trace which now looks, of course, specific to the acetone all the butadiene. And now if I have the mixture, I can sort of try and infer. And this is now the result which just appeared now in Nature Communication. And I really want to give credit also to Davide Pinto, who really worked a lot on this and were crucial for this experiment. What they did now is they measured as function of time what the intensity was and the famous trace, and they reconstructed from the fit, they reconstructed the spectrum as function of time for these two. I mean, you can either do a so-called targeted reconstruction, meaning you know what you have, but you don't know how much. And this, of course, gives you a much better estimate than I don't know what I have, and I'm trying to reconstruct the spectrum just knowing what the trace is. And those are the meaning of this reconstruction A and reconstruction B. So, but you see that in a way, they really got some extremely good results with that. So it's very exciting because it means that in principle, you could do broadband spectroscopy with just one comb, one detector, an interaction cell, and some RF equipment in between. And now you don't need a fast detection. It's just, you know, so conceptually it's very nice. Now I see I'm running, yeah, I still have 10 minutes, and we'll want to leave time for questions. I'm going to go a bit faster on the last topic because I still want to mention it because, you know, so far, of course, the understanding was when we were presenting the quantum cascade laser was always, you see, there is interband transition. Interband transition, you know, the lifetime is long. Why? Because if you have a clean material, the only way the electron can go down is by recombining with the hole, and that takes time. And, you know, you have this very efficient transition. And there is the intersubband transition, which is nice because it's flexible, but you have very challenging because the lifetime is very short. And so, of course, you'd say, well, we saw that the intersubband transition is very good for quantum walk because actually you need a very fast gain recovery time to do a quantum walk. And so you'd say, well, that probably is that interband device, the interband transition bad for quantum walk. And some papers, of course, in the literature, they seem to say, well, you know, this lifetime is very long, and therefore, you know, we should not see quantum walks. But that is actually not true. It's actually not true. Why? Because you have to be a bit more careful. What is the lifetime? And it's actually well known, and for a long time, people are using, of course, in quantum cascade laser, you can measure the lifetime. You find it's very short. That's well known. But if I take now a amplifier, a semiconductor amplifier that you have in telecom, you know, and people have done 20 years ago already, those measurements of how fast does the gain recover in such an amplifier. And what you see is, well, actually, initially, it recovers very fast. Why? Well, because there is a lot of physics that is very fast. If I come and deplete electrons, you know, if I have this interband transition and I come with a strong pulse, I'm eating a spectral hole in my conduction band, and that spectral hole will be then refilled by processes that are very fast, electron-electron interaction and optical phonon. This is even faster than quantum cascade laser in that sense. And the question then is, well, of course, the interband cascade gain recovery lifetime is a mix of long and fast comparison. So, you know, we're trying to test this idea. We said, well, we're not in the business of manufacturing interband lasers at 1.55, so we bought a gain chip, a BOA from Tor Labs, put it in the cavity with an isolator just to make it run in one direction. And, well, very simple thing. But then, you know, you basically take that gain chip, run it, put AC on it to modulate, and guess what? You see a nice quantum walk. You see the exact same broadening and narrowing of the spectrum as function of frequency as you saw in the quantum cascade, quantum walk. Okay, it's a bit more sensitive, but it's really nice because the RF bandwidth is extremely narrow. You know, it's just completely slave to the drive. You can also drive it in harmonic. In harmonic, there we went sort of, again, was really not optimized for RF. We drove it, the fundamental spacing was about a gigahertz. We moved it to 13 gigahertz. and it still gives you this nice quantum walk. And so, of course, that was a, it got people interested, and the postdoc, Bahar, she started a company called A-Light, so it's a startup, which we're trying to use this quantum walk for datacom and do telecommunication. So with that, what I really hope to show is that, you can do quantum walk using semiconductor lasers, because semiconductor gain, because they have a fast gain recovery mechanism, and they tend, therefore, to attenuate pulses, and they like to mode lock, but not with pulses. And that, of course, in a sense, it is a bit challenging, but I didn't have time to show, but we have shown this also in the terahertz, also at 5 microns. So it's really it really works at all frequencies. And, you can think of it, I would call it a liquid comb. There is, on one hand, of course, the idea that you can, if you think, how do you do a classical comb? Well, you could say, I have a slow gain and nonlinear resonant Kerr effect, for example, and that gives me pulses. But, the idea here is that the liquid comb is, you basically have gain, which is also gives you this saturable absorption, which stabilizes the comb, and you inject the RF tone such that you stabilize the comb using the RF injected. And that is stabilized by the gain. And there's also all sorts of aspects, which I have not time to discuss, which are a bit more, you can map also the system to a block oscillator, and you can do all sorts of things. And so as a conclusion, I hope to show you that, we had optical frequency combs for spectroscopy, and that they are ruler in the frequency domains. You can do all sorts of interesting applications for them. And that the key ingredients for the quantum walk comb is the fact fast gain dynamics, break time reversal symmetry, and you do a phase modulation. And now quantum walk really arise in semiconductor lasers, both in QCLs and also interband devices. And then you can have application for dual comb, for single comb spectroscopy. And with that, I would like to thank you for your attention, and also thank my group for all the work that I've shown today. And welcome all questions. Thank you.
So we have an opportunity for questions, and also we have a nice cube, soft one, if you have a question, so please. Yes.
So question in real life, we're talking, so the cycle of the one period of the broadening of the comb, how much it takes? So it's 10 microseconds roughly, isn't it?
So the base frequency of this quantum walk combs is typically, the repetition frequency is gigahertz to 10 gigahertz. You can typically, let's say, a quantum walk, I would be a bit skeptical of trying to make it too slow, because, of course, since you're propagating line by line, at some point, we have not measured that, but I would be afraid that you would start to be unstable. So those are combs which have typically 10 gigahertz. Now, the time that you saw, the microsecond, was the time relating to how fast it reacts. And that reaction time, of course, is related to the expansion time. So you see, I showed you the let's say if I look at the famous quantum walk right here. You see, when I turn on my RF, I basically have something like 250 nanoseconds to establish.
Okay.
And so that's, I don't know, at 10 gigahertz, that's maybe 2,500 round trips. So the 10 microsecond is basically, it's not the fastest, but it starts to be where, let's say, your comb reacts and nicely follows the frequency that you send.
And what is the operation mode? In this case, QCLs operate in continuous wave?
Yeah, you need continuous wave to be stable in narrow band and also narrow line. This is operated at -20 or so to have a bit more power and a bit more operation.
Okay, thanks.
Mm-hmm.
So another opportunity to play with the cube. Yes, please.
Yeah, thank you for the nice talk. I actually have a question about this slide in particular. So the simulation of the quantum QCL walking home. So the theory shows that you have an even, a nice splitting between the, I don't know, first mode and the 40th mode. But then in the experiment around the 0th mode, you see some emptying. So what's the deal with that?
That's a very good point. Look, it was a bit of a headaches for us. The problem is the switch, the RF switch. So you see, you're turning on the RF and then turning off, and your measurement is much slower than that. So the problem is we have leakage from one situation to the other one. And the dynamic range is, of course, enormous because all the energy of the single mode, now you're putting it across so many modes. So even if you have 30 dB rejection, you still see the peak. It's really instrumental. This thing is not there.
Okay, thank you.
Yeah.
More questions?
Okay, so thank you for a nice talk. So basically you showed that quantum walk is possible when you have parabolic potential, yes?
Mm-hmm.
So what if you would have rectangular potential? Is it possible or
that's
not?
a very good question. I mean, the shape of the parabola arises because of dispersion. Huh? So now, and the very, very good question is, yeah, but what about third order dispersion? And in a way, this is exactly, if you want, the place where it hurts a bit. I said, and then we were so happy because we said, cool, when I was showing this, for example. We said, ooh, great. You have this square root of m over d, so make d very small, and you need tiny width of modulation. You get this immense broadly combed. Yeah, except that if you reduce the second order dispersion, you're not reducing the third order dispersion at the same time. So your nice parabola becomes like a tilted third, a cubic type. And there, let's say the dynamics of your comb is different. And you can simulate it, and we're actually looking at it. It definitely explains a lot of the kind of strange things we see in some of those combs. And our conclusion is, yeah, you need enough second order dispersion to make sure and actually try to eliminate as much as possible third order dispersion such that you have this nice behavior. And if you cannot control your dispersion well, then you are in trouble because then you sort of start to have another dynamics that is not as nice as the one that you have in the parabola.
Okay, thank you very much.
Someone else?
But yeah, one thing I want to add on this, of course, what is nice also, and I haven't time to talk about, is you can think, yeah, you can inject 1F, but you can also inject 1F and 2F. And now you have interference between these. So you can, instead of just connecting two adjacent nodes of your synthetic space, you can now do bridges. And now the nice thing is you can have even a better control of your spectrum with that. And so we showed that you can actually basically now steer the spectrum even very strongly, not by changing the center frequency, but by changing the phase between the injection at 1F and 2F. And it's really like a bit like you can really map it into kind of a topological, grid in which you're sort of changing the phase of kind of a bit of a similar to the Haldane phase in plaquette. So it's kind of it's a nice toy you can play with. Yes. No, I mean, what I find very, very interesting in this is that you can use the RF to shape the optics, and so, yeah.
Thank you. Next question, please. Maybe can we spy a little bit about this 3 terahertz antenna in one of the last pictures? It's unpublished, but maybe something can be
the 3 terahertz quantum walk.
I think it was the last with some nice spiral-shaped antenna.
Ah, I see what you mean. Sure, of course. This one, yeah. This is, okay, had a very creative, this is the work actually of my colleague Giacomo Scalari. Yeah, the idea here is you have a ring terahertz QCL and you're trying to excite it as efficiently as possible. And so the idea is to sort of pick up, the thing that is running around and couple it to an antenna that radiates, And of course, you work it also backwards, and you sort of inject in that antenna RF, and then you sort of can drive your quantum walk this way. Yeah, that's the idea. And we should publish it at some point. I mean, soon.
Yeah, it's very nice.
Absolutely.
Yeah, please.
Thank you for the talk. I have a practical question. So what is how broad it could be made a spectrometer with this technique? Because as far as I understand, so we have some limited range of spectrum, and how realistic is to make a device that can compete with traditional pump probe?
So, I mean, it's still a bit of an open question. And let's say, of course, we had great hopes. We could sort of break the 100 inverse centimeter barrier and go to 200 inverse centimeter. It's not so easy. And it's not so easy because, in a way, again, it is really a lot of engineering that you have to be very careful. I honestly don't know, because in a way, we still had those, I mean, at some point, Outlaser did those really nice, very, very broadband lasers that were basically to 250 inverse centimeter continuous wave of the whole bandwidth. Now, the question is, can you sort of operate those in a quantum walk comb? And that would need, you see, the issue is that to make that feasible, you need this very nice gain, very flattened. You need also a very nice dispersion, and you need a very nice RF injection capability. So I still believe if you can put those three things together, you're going to go higher than the 100 inverse centimeter that we showed, which in the end was just with one, I would say, a reasonably optimized, but certainly not longly optimized device. It was just first try we did. So I think there is a chance, but of course, there are limits in a sense that you can also show theoretically that the lifetime, one over the lifetime, or let's say, gives you a measure of the maximum bandwidth you can reach. Because this is the thing that stabilizes. What stabilizes the comb, in the end, is the fact that you absorb those very fast fluctuation, and that your gain recovery time, if you want, eats away those fast modulation. That's what stabilizes the comb. And of course, it needs that the gain is fast enough to do that. And so that's why I would say, between 100 and 200 inverse centimeter, that's probably where the limit is.
Thank you.
Thanks. Do we have more questions? So it seems that we are running out of questions. So let's thank the presenter again. Thank you.
Thank you.